now let us come to that. So, to keep things very concrete, what I am going to do is I am going to assume 3 segments, okay, just 3 segments, and we will build our system of equations for 3 segments. For these 3 segments, so what we will call them is, this is element 1, element 2, element 3, okay, and this is node 1, node 2, node 3 and node 4, okay. So, what are my shape functions like? How many shape functions do you have for this 6 shape functions, okay. So, what do they look like? Right. So, this is my ui, I is equal to, so this is what did we put it like this, right, I and E. I is equal to 1 to 2 and E is equal to 1, 2 and 3. So, total of 6 shape functions. Okay. So, with this in mind, how do I write the field? I write the field u of x in terms of these basis functions, right. So, it is a summation, and this time we will explicitly open up the summation. Okay. So, the first unknown, let us write the unknown and then the shape function. So, first unknown, okay, let us get rid of this summation. So, is u11 multiplied by n11, correct, x. Next is going to be u, so 1 on top and 2 below, n12 x, right. What else? The next I go to u21, n21, u22. Now that you get the hang of it, you can write it quickly, okay, plus u31, n31 plus u32, n32. Okay, all of this is function of x. This is how you would write it. Okay. Now, of these variables, some variables are the same, right? These unknowns, some of these unknowns, so these are unknowns, right. Of these unknowns, some of the unknowns are the same. Which are they? u21, u12, what else? u22 and u31, right. So, the common variables, let us just indicate them. They are the same and they are equal to u2 and u3 respectively, okay. So, what you could do is just a way of rewriting this. If I wanted to write it in terms of moving from local to global, if I wanted to rewrite it, I could write it like this: u1 n11 x plus u2 n21 x plus n2 12x, right, plus u3 n21x. Have I made a mistake somewhere? Yeah, this should be n22 actually. Plus n31x correct. So, this was the first one was local, the other one was global, okay. u4 this should be. Local and global what? Unknown numbers. Now, these two functions over here that I have in these green brackets over here, if if I want to plot them over here, let's try to plot the functions that I have shown highlighted in green over here. Okay, so some of you see where this is going. So we'll draw it a little bit bigger here. 1, 2, 3 and 4. Okay. So the first one, n1x, which way is it opening? Is it left or right? n11x, this first term over here, left, right? So this is what it looks like, 1 at this point and this thing. This is my n11x, correct? Agree? What about the second term in the green bracket? What does it look like? It's a sum of two functions, two triangles, one opening to the right, one opening to the left. So it's going to look like correct. I'm going to call this let's call this T, let's call it T2. The next term in the brackets again is going to look just like this one, except it will be shifted by one node, right. This is going to be my, I am going to call this T3, okay. And finally the fourth one over here is going to be my usual N32, that is right opening third segment. Okay. So this guy. Okay. So how many unknowns did I have in the global, in the overall problem? U1, U2, U3, U4. Okay. So the reason that I did this combination is because remember I have 6 shape functions. If I do my testing with all 6 shape functions, what will I get? I will get 6 equations for each one of them, one for each one of them, but how many variables? 4 variables, right. It will turn out, and you can work this out, it will turn out that 2 of those equations are redundant. They are just formed by taking a linear combination of some of the other equations. So to avoid having to do that, what I've done is I've combined adjacent shape functions into, for example, here T2 and T3. Okay. So these above over here, these are my shape functions, and these guys that I have drawn over here, these are what I will make into my testing functions or weight functions. Okay, this is still Galerkin's method because the shape functions and the weight functions are the same. What I am giving you is a bit of a shortcut, one shortcut compared to what most of the books have. Most of the books will make you go through 6 equations, 4 variables and then eliminate and come back to 4. What we are doing is directly arriving at 4 because we can anticipate what is going to happen. Okay. So these are the 4 testing functions. 4 testing functions, when I apply it to my equation, I will get 4 equations, 4 variables. Okay. So in general, this is a strategy. I mean, if you look at it, how did we combine this? Wherever a node was shared, I combined the shape function. That is what I did. The endpoints could not be shared, so they remain as they are. Okay. So now let's go step by step. Let's do testing now with respect to each of these basis functions. Okay. So let's look back at our equation over here. So okay, so let's write this down over here. So the first term is w prime x u prime x minus, this is a minus and a plus k naught squared wx ux is equal to the endpoints term, right. So, this is equal to minus Wx u prime x. Okay. Why did I move this term to the right hand side? Because we should know this. U prime x is where I am going to impose my boundary conditions, which I derived, and its Wx is of course known. Now, without doing this end, so this should be done for every W that I take, I will have this endpoint contribution. Can you look at this and say which all endpoints will appear in the final equation? Okay, we will come to it as we start calculating it. We will come to it. Okay, so let's do testing with. So the first weighting function, which is equal to n11, that's my W1. Okay, that's what I'm going to do. U continues to be, so u of x, we will continue to write it as in this form, right? U I E n I E x. That is what I will write it as. Okay, and this is also equal to, in very short compact notation, what is this? U1 n1 plus u2 t2 plus u3 t3 plus u4, let us call it n4. Okay, actually n, yeah, fine, we will just call it n2, n1 and n2 and t2 and t3. So what do we get with when we test with n1? We just shorthand notation for this n1. Okay, so yeah, let's make it k square. Yeah, there might be an epsilon inside, so that will be absorbed inside k square. So, we will just leave it as k squared. K squared is in general position dependent. Yeah, otherwise this is empty space. Then we should include, correct, you are right. Yeah, good. Yeah, I mean, if epsilon is 1 everywhere, it's a very uninteresting problem. This is free space that I am simulating, right? But in our case, there might be an object in between, and that k will have epsilon mu inside it. Okay, we are just keeping it as k squared for now. So this is a function of x. Okay. Okay, so what happens to the first equation? So what is going to be W prime and U? So okay, what is W1 prime? And constant equal to what? Minus 1 by, no, the nodes are not equispaced. I mean, they are not spaced by 1. Remember the definition of n1, right? It was what was it? x2 minus x divided by x2 minus x1, right? So if I call this spacing to be some delta, right? So then W1 prime x is going to be equal to minus 1 by delta. Okay. Alright. What about U prime x? In this, and this integral is over which segment now? This integral is going to be only over segment E1. All other segments are 0 because W itself is 0 outside it, right? So the derivative is also not defined outside of it. So U prime x, this is my U over here. So which all terms will appear in U prime? Or you can look at this form, okay? Look at this form of U of x. Now you have to evaluate U prime of x. So what will happen over here? So let's write it down. Minus integral of over E1. W prime x is, we said, minus 1 by delta, okay? U prime x. So I have to take the derivative of this term and this term, because both of them are non-zero in E1, right? These other terms will not appear because they are not in the support. Delta is the width of the segment, this delta which I have marked over here. Derivative. I have W prime x, right? This is W dash. Yeah. It need not be the same. The lengths that I have shown are equi-spaced over here, but they need not be the same, okay? So instead of delta, I will write delta 1, okay, minor details. Okay, u prime x, what do I write in u prime x? What is the derivative of n11x? Minus u1 divided by delta, okay, and plus u2 by delta dx. Other terms are not going to appear. Then I come here, k squared. Now I have wx multiplied by ux. So what is this going to be? Wx is n1, right? So in this notation it's n1. So wx is n1 squared plus n1x. Actually, I should write it a little bit more carefully over here. Is the product of n11x with the other two terms. So there's going to be u1 n11x plus u2 n21x. Sorry, correct? Dx and the endpoints term. Okay, so what can I say about the endpoints? At which points am I evaluating this? At u1 and u2 is where I have to evaluate this. Okay, so the first is, so this is going to be at node 1 minus node 2. That's what it is going to be. So what is the value at node 2? This is node 2. At node 2, what is the value of wx at node 2? Wx is my n1x, 0. So I have a minus 0. What is the value of wx at node 1? 1. What is the value of u prime x at node 1? It's a trick question. Minus? Trick question. u2 is not going to appear. So all of you, what you are doing is you are looking at the form of ux, you are taking the derivative and telling me what it is. Forgetting that, why did I move this term to the right hand side? It should be known. So known is coming from where? Not from the form I have assumed for ux, but from the boundary condition. So what is my boundary condition? Let's go back to it. Boundary condition is u prime x, right? So u prime x is equal to minus j omega, let's just call this whole term some alpha, okay. So is equal to alpha into ux. I have to use this, otherwise I mean I'm not imposing boundary condition. So okay, so wx at the boundary is 1 and u prime x is going to be alpha times 1. So boundary point node number 2, this is node 2, that has no contribution. Node 1, u prime is equal to alpha ux. What is ux at node 1? Yeah, but what is that? u1 with an alpha minus alpha u1. I have to substitute here, this is an endpoint substitution. I have to substitute the value of ux at node 1, and I, by definition, the value of ux at node 1 is u1, and there is an alpha that came from the boundary condition, right. So where did the wavelength and all of those parameters, where did that go? It got absorbed into alpha, right, the frequency and all that. So the incident frequency is appearing somewhere in this equation, right. So it's not gone. So this has come from node 1. So what does this look like? This equation that I have written over here, can I solve it? I mean, can I simplify it rather? What is, let's go term by term. What is this expression over here? In terms of x, is it a function of x? No, right. So this is a constant with, there is a u1 and a u2 there, right, and integrated over dx, so just the length of the segment will come. What about the second term? So this is also integrated over e1. What polynomial is this? Is it constant, linear, quadratic? Quadratic, right? N1 is linear and N1, N2 are linear. So, this is a quadratic function. What are the variables? U1, U2. Anything else is a variable k. K is a function of x, right? So, if my discretization is fine enough, I can assume k to be approximately constant within that. So, piecewise constant approximation I can make for k. Or if k is something more complicated, there is no problem. What will I do for this term? Use a quadrature rule in general, right. So, this can be evaluated by quadrature, right, fine. And from here what will happen? U1 will be taken back to the left hand side, okay. So, this there is a little bit of a there is a little bit of inaccuracy in what I have said so far in evaluating the boundary condition, okay. I have written it as alpha times U1, but there I need to modify this a little bit, okay. So, let us erase this for now. This 0 term is correct, this alpha U1 is needs a little bit of a modification, okay. So, let us just look into that modification before we go further. So, let me erase that for now. This boundary condition, the intuition is correct, right. So, what is this saying? That at this, let us say this is the boundary, the wave is going in this direction, and at this point I am imposing this boundary condition, okay. Similarly, at the left boundary, same thing is happening, I am imposing this boundary condition. Now, this boundary condition applies to what all? Does it apply to, let us draw our object over here, okay. So, the same antenna problem over here, human being over here, right. So, this guy is sending out, let us say, an incident field. Let us read right over here, okay. So, I have my antenna over here, and what is it doing? It is sending out a field like this, let us say, okay. 1D problem, so I am trying to draw it in 1D, okay. I have my object over here, okay. These are the two boundaries of my simulation domain, fine. What is happening is that this wave is entering inside over here, getting scattered over here, going through over here and then going off over here. This is physically what is happening. Now, the intuition for the boundary condition that I had given you was that the field should not reflect back from this hypothetical boundary, correct. At this point, what is the total field? There is a scattered field that is coming from the object and some part of the incident field. Both of them are outgoing and both of them should not be reflected back, that is what we want, okay. So, here there seems to be no problem, but when I come here, what is happening? Incident field is actually going in the opposite direction from outgoing. The scattered field is the part I should not allow to come back into the simulation domain, right. Incident field I do not care about, it is given by a mathematical expression. So, this boundary condition that I am saying, that no reflection from the boundary should be applied to the total field or the scattered field. Scattered field should not reflect back. Supposing I delete the object, then there is no boundary condition to impose. Incident field can enter from one and exit from the other, and that is consistent. But scattered field is always going out. We are assuming that the object is fully contained inside the simulation domain. So, what is fine? Exactly, the scattered field is outgoing, right. So, here the scattered field is outgoing, here the scattered field is outgoing. So, the boundary condition should take care of scattered field, not total field. Now, what are the variables that we have chosen over here? What are they? Total field. So, should we be imposing the boundary condition on total field or scattered field? We should not be imposing it on U, we should be imposing it on scattered field, right. So, this boundary condition over here was, let me write it as this, E scattered is proportional to, this is the correct boundary condition. This is what simulates a wave not coming back, going on forever, free space. So, in terms of u, what will I write this as? So, E scattered, so we know that E total is E scattered plus E incident, right. So, all I have to do is, since my variable is E total, so E scattered will be u minus u incident, right. So, this is equal to E scattered. Okay. So, now let us use the boundary condition. So, boundary condition is saying d by dx of ux minus u incident x is equal to alpha times u x minus u incident of x. Right. U incident of x, we will assume is given to us, it is a plane wave or whatever, I know the functional form. So, when I simplify this once more, what do I get? D by dx, finally see in this equation you see I want a condition on u prime x. Okay. So, this is the important thing that we have to keep in mind. So, the right hand side which I evaluate now, which now that I have done it a little bit more carefully, node 2 still gives me 0 as before, and node 1 over here, this is what I will replace from here. Okay. So, what will I get? I will get a minus some term over here, there is a minus minus which gets combined into, what will that term be? Is equal to, it will simply be, so what is this term evaluated at node 1, right. So, alpha times u1 first term plus u incident x at x is equal to x1 minus alpha u incident x at x is equal to x1. Yeah. Yeah, incident field is going to be given to you, we will assume that. That is also we will calculate it, no. Supposing I give you ux is a plane wave. No, we are not computing the incident field, it is given to me in functional form. For example, u incident can be e to the j k x minus omega t or some other complicated function, because it is like the given in the problem, the current source is given to you, you can calculate what field it produces in the absence of object, that is given to you. Fine.